All right, so my name is Miguel Murillo. My other partner's not here. I did thermoelectric, thermal conductivity through the 3 omega method. So what is a thermoelectric? A thermoelectric is a device made up of two dissimilar metals that can create an electrical current if a temperature gradient is applied across it. Conversely, a thermoelectric device can also create a temperature gradient if an electrical current is applied through it. So some of the people that contributed it was Thomas Seebeck in 1821, and he found that an electric current would flow continuously in a closed circuit made up of two dissimilar metals if the junction of the metals were maintained at a different temperature. And a French watchmaker and part-time physicist Jean Peltier in 1834 found that an electrical current would produce a temperature gradient at the junction of two dissimilar metals. So some of the applications of thermoelectrics: power generation in radioisotopes, nuclear reactor systems, engine exhaust, and process industries. Another application is thermoelectric heating and cooling for temperature and climate control. Other applications would be cool car seat, electronic cooling, and cryogenic IR night vision. So our objective, one of the most important components that when making a thermoelectric device are the materials that you use to make it. Material properties can vary greatly depending on the material that you use. When measuring the properties of a material, thermal conductivity is one of the hardest properties to measure. A proven and reliable way to measure thermal conductivity is by the 3 omega method. Our objective will be to make a device based on the 3 omega method to measure thermal conductivity of thin film materials. Also, a user-friendly interface will be made to facilitate the process. There's currently no device like this out there, and we believe that it will facilitate and speed up research and development of thermoelectrics. So the 3 omega method was developed by Burge and Nagel in 1984, and back then they only used it to measure frequency-dependent heat capacity. The 3 omega method was first used to measure thermal conductivity by Cahill in 1990. Experiments were performed on a wide range of materials, including nanostructured materials, such as two-dimensional superlattices. The 3 omega method consists of sending an AC current with a frequency omega to the sample. The output voltage will contain a 3 omega component superimposed on the initial omega voltage because of the temperature-dependent electrical resistance of the sample. The 3 omega component amplitude is about 1,000th of the original signal. Our goal is to cancel the omega component of the output signal to increase the ratio to the 3 omega of the omega voltage. The 3 omega voltage has the information about thermal properties of the material. Once we have the 3 omega voltage, we will be able to measure the temperature oscillations of the material and be able to accurately calculate the thermal conductivity of the material. And that's my references.